Now that we've got our formula, the force of buoyancy is equal to the density of the water times gravity times the volume of the water that was displaced. Come to like a historical moment. Archimedes, the ancient Greek, did a lot of experiments and invented a lot of nice little things. So there was a principle, and the principle is this. The buoyancy force, he figured, actually calculated, is equal to the weight of the waters displaced by the object itself. So what he's saying is the buoyancy force is equal to the weight of the water. Now, here's a comment here. We're talking about the water displaced by the object. So, for example, when we were talking about the can that was submerged under the water, it's the weight that of the water that the can actually pushed out of the way. So, let's say, for example, we had a tank of water, filled it all the way up to the very, very top, stuck the can in the water that ran out of that, we could collect into a little basin, put it on the masser, and then at that point in time we could actually weigh it. Well, the weight of the water that was pushed out by the can over the sides of the container, if we took that weight, is actually equal to the amount of the buoyancy force that we've calculated. So, if we look here, Archimedes is saying the buoyancy force is equal to the weight of that water, pushed out of the way by whatever object you put in there. All right, let's see if this is actually true. Well, we know that the buoyancy force is rho GV, so let me write that underneath here. So rho GV is equal to mg. All right, let's see if it's true. Well, oh yeah, isn't density equal to m divided by v? So if we look here, let's replace the rho with m divided by v, g, v equals mg. All right, let's cancel out the v here, the volume here, and the volume here, and we're left with mg equals mg. Yeah. All right, so the weight of the water is actually equal here to the weight of the water on that side as well. So Archimedes' principle really does make sense. Now, if we look here, let's try an application of these principles. So if we look here, let's try dropping something into water and see what happens. So if we go to a lake, and what I'm going to do is take a rock, very heavy. I know it's going to submerge completely under the water because the density of the rock is actually heavier than the density of the water itself. So we attach the rock to a string, a rope or whatever, and we're going to stick it under the water on the string like so. The question is, how much force do we need to actually hold up this rock? All right, now, the rock itself is 70 kg, and I'd like to know, well, hey, what does it actually feel like as we're holding this rock up? Well, we're a little smarter now. Don't we know that the buoyancy force is actually helping to support the rock? So it's going to feel actually a little bit lighter than you would think. All right, now let's get our forces pen out and then draw the forces acting on this. So we know at this point in time that the rock itself has weight, mg, pulling downward. The rock displaces water. The water would be the exact same volume as the rock itself because the rock is actually under the water. And we're going to get a buoyancy force that is up this way. So our force of buoyancy is this way. All right, now, I don't think the rock's going to float. So if we look here, which of these two forces is going to be bigger? Well, guess what? When I'm dealing with a rock, isn't the weight of the rock stronger than the buoyancy force? So I'm going to have to pull up on the string. So we have a tension force pulling upward by the rope. Now, if you think about it, isn't that tension force getting a little bit of help from the buoyancy force? I don't have to pull up so hard because the buoyancy force is actually trying to make the rock float upwards, and not successfully, but at least partially so. So I don't actually have to pull so hard on the rope itself. So the question is, well, what is that tension? So let's take our forces and let's add them up. So as we pull up here, we take a look, and the net force, of course, is going to be 0 here. So our force is, tension is up. FB, that's the buoyancy force, is also up. And mg is down. If I solve this for the tension, how hard I have to pull up, let's do that. So we've got the tension is going to be equal to mg minus the buoyancy force. Well, yeah, I think that makes sense. All right, how hard do I have to pull up on the rope? Well, normally I don't have any buoyancy force when it's not under the water, but now I've got the buoyancy force helping me, so I don't have to pull up so hard. So you take the weight minus whatever the buoyancy force is actually helping me. So let's see if we can actually calculate what this is. Well, we need a little bit of information. We need the mass of the rock, and we've got that. So the tension is going to be equal to 70 kilograms times our 9.8 meters per second squared. The buoyancy force, we have a nice little formula for that, is rho GV. All right, now we need the volume of the rock. I don't really know what it is. Let's just make one up. All right, so I'm putting down here the volume of the rock is 0.03 cubic meters. Where did I get that from? Who knows? I've got it. I can measure it. Maybe I could use water displacement, something like that. So this is our volume right here given. All right, now that we know all of these, let's put it together. So I've got the 70 kilograms times 9.8 minus the density of what? What's creating the buoyancy force? It's not the rock. It's the water. The water pushed out of the way by the rock. So this is the density, not of the rock, but of the thing creating the buoyancy force. It's the density of the water, which happens to be 1,000 kilograms per cubic meter. All right, G is 9.8. The volume of the rock is 0.03 cubic meters. And if we solve that for the tension, according to my superior calculations, I've got an answer of, looks like 400 newtons. So let's hope that's right. Punch that in a calculator, and then you can check to see if I'm approximately correct. So the tension on the rope has been reduced. Normally, if I'm holding up this rock, isn't this going to be 70 times 9.8 mg? So it's going to be around 700. So the tension on the rope has been reduced now to only 400 because the buoyancy force is trying to help me out. So this is a good example of some application of this buoyancy force and how the buoyancy force acts when we submerge things under the water.